All right, so to sort of show you the problems I'm having with the fourth order RC filters, I brought us back into Code Composer. Right now, I have the impulse invariance fourth order bandpass filter with a cutoff frequency of, or a bandwidth from 100 hertz to 3000 hertz. And the sampling frequency is 8000, so lowest sampling frequency. And we're pretty much including most of the audible spectrum, from 100 to 3000, where the whole spectrum is from 0 to 4000. So, I mean, I don't know. It's not the cutoff frequencies that's causing this problem. It's something else. As I've shown in MATLAB, the simulation part works in MATLAB. If I run a test signal through MATLAB, we get the results we expect. We see the signal attenuate. Because our test signal is in this stop band. But here we get this whole issue with some sort of maybe rounding error. I'm unsure. But if I go ahead and just restart this temporarily, if I hit run, pay attention to the output buffer here. Why? Right now it's all zeros, of course, because we just reset the program. But once I hit run, it's going to grab a few of these values before it loses track, and you know that might be hard to trust, but just watch. So I'll hit resume here, and you know it updated these quickly before completely losing, like letting it go full on. And what it grabbed was, here are some input values in the input buffer, and then in our output buffer we get nan, or not a number, values. And this can happen whenever our output values end up blowing up to infinity, like we would expect from an unstable filter. But as we saw in MATLAB, the filter is stable, and even simulating it, just like we would on the DSP board, it works. And I think the main difference between MATLAB and the DSP board is the DSP board is having to do some rounding in order to do the operations I'm asking it to do, whereas MATLAB can probably get away with less rounding because it's running on a 64-bit processor. I don't know. But regardless, we go ahead and hit stop here. Well, that's interesting. Look at that. We have, so I think it grabbed one of the input values and threw it into the buffer. And you can see it made it there, but if we step back through this, yeah, it's already back to not a number. I meant step through, but I hit resume on accident. But regardless, this is what happens. I've made a few changes to the code in terms of precision in order to sort of alleviate this issue, and it worked for the other filters, like the LC filter had this issue. But what I've done to make those work, and what I thought would help this RC filter work, was to change all of my floating point numbers from single precision to double precision, essentially doubling the amount of memory that they take up. So before, if you looked at the output and input buffers, you'd see them, you see it go from like A0 to A4 to A8 to AC to A to B0, which means that they're essentially, the floating point numbers would only be taking up 4 bytes, but now you can see they're taking up 8 bytes because this first element has an address space from A0 to A8, whereas before it was only A0 to A4, for example. So this really only happens after doing the fourth order business. If we run through here on MATLAB, and let's say I just do the first order filters, same sampling frequency, same cutoff frequencies and everything. It's going to attenuate less, and there's a plot in MATLAB that it's actually showing it only attenuates about halfway. So let's go ahead and restart. Let's check our coefficients first. Yeah, those definitely changed. So let's go ahead and restart the debugger. And it'll go ahead and build for us. We didn't see any errors, so everything's fine with regards to the code. It's just runtime problems. Any day now. I'll try that again. There we go. All right. And we will run and we'll stop. And if you look in the output buffer, you can see we don't have any nans, which is great. So what I did is on MATLAB, like I mentioned, I just took the single order filters. I didn't essentially convolve them to make them fourth order filters. So yeah, simple hardware limitation. I don't know. Maybe if I switched up back to the linear filter or the linear buffer instead of the circular buffer, maybe that would fix it, because maybe somewhere in here, a lot of this for looping in the input values and then for looping through the output values by themselves allows the numbers to blow up super big. But I don't see why that would. I don't have a gut. I have a gut feeling that that's not what's doing it. I think it's simply just not able to handle fourth order filter. If let me load up the fourth order filter again, and I'll show you something else too. First off, let's look at this right here. So this is what I want you to see. Look at these are the denominator values of our filter, right? They're 1 and then -1-ish and then about 0.1. So relatively small. If we go ahead and bump up to the fourth order filter, you'll see these get pretty big, relatively speaking. Some of them, actually. Well, that's not too bad. So you see some of them jump up to 6, some of them -5, and you know, I've done some testing on the single order filters, and I can get those to mess up too, and get not a number of values in the output buffer. So even using the lower order filter isn't perfect. And I've noticed that the lower order filters break whenever these denominator values in our filter are really high, or at least bigger than 1. As you'll see or have seen in MATLAB, I've also got a zero pole plot showing you the poles that are inside the unit circle, and how that really indicates that this is a stable filter. But yeah, hey, that's promising. Can we keep that? Oh my. Well, okay. This is bizarre. We're gonna let it run. And it sure is running on my computer. So I don't know why it's running. Sometimes maybe, sometimes you just get lucky. Here, let's try to break it. Let's try to break it now. Now that we have it working, see if just restarting things breaks it again. No, it said okay. It said I'm fine now. I wasn't 2 seconds ago for no reason, but I am now. All I did was, gosh, all I did was make them fourth order filters again. I swear. Debugging this thing is such a pain in the butt. So now it's working. Why is it working? Oh man. Let's just reload the filter. I don't think anything's gonna change. Okay. Restart the debugger here. Oh boy. If it's just like the DSP board being a pain in the butt, I wouldn't be surprised. Okay. Let's keep going. Yes, look at that. No nans this time. Okay. Let me go ahead and increase sampling frequency. Save it. And I'm going to load up the filters at a higher sampling frequency as well, 12 kilohertz. All right, it's loaded. 0.3, yep, those all changed. Okay, and it works. Can someone stop pulling my leg here, please? Okay, back to 8,000. This is for the impulse invariance technique, and I didn't notice too many problems with that. It was mostly having problems with the bilinear transform. So we're gonna change out to the bilinear transform real quick. That's pretty much taken care of now. We have different filter coefficients. I'll show them here. All right, and we're back at 8,000, so let's bring this back. Double check to make sure I put 8,000 in MATLAB, and yes. Okay. So restart the debugger, or just basically restart the app with the new binary file. Now I should get some nans. Yes, that's what I like to see. Some good old not numbers, because who needs not numbers? Okay, and then I'm going to switch back to impulse invariance technique. And if this happens like before, it should break still, because that's what happened last time. I simply switched to impulse invariance technique and it just broke. It was still broke. Okay, yeah, we can see the Duke new coefficients. That means we switched up the filters on MATLAB. Now, bam. And of course, it works. Okay, so, well, this goes to show you that the bilinear transform still does not work. but the impulse invariance technique does. Now, to really push the limits and see if we can break it again to confirm that this is a hardware limitation, I'm going to increase the sampling frequency of our filter, which hopefully will cause enough rounding errors to get us more nans. Let's bump it up. Let's just open it wide. We'll go to 96 kilohertz sampling frequency. We'll keep the same filter bandwidth, 100 to 3000. And we'll still be using the impulse invariance technique because we want to break this one. We want to show that this is the rounding problem. Okay, new coefficients. Got them. Change the sampling frequency. Save it. Open up that. It's not really necessary, but we'll debug now. Yes. Yes, I want to redo the debugger. I did not misclick. All right, we're back. And wow, look at that. It just works. It's incredible. What is this? Where are you going? I said I caught it in a different header file. That's funny. Yeah, but as you can see, our output buffer isn't getting nans. If I just let it run here, I'll show. I can look on my desktop to see the filter working, and yes, the filter is indeed behaving as expected, unfortunately. Okay, I am simply going to stop this here and proceed with the demonstration on the desktop. This was a productive session, for sure.